about continuous probability distributions today. This is a new topic. The main difference between discrete and continuous probability distributions is that discrete ones refer to a finite set of variables we can actually match to our x. Yeah? So we can list all the possible events for the discrete ones, which is where we use binomial or Poisson. In this case, where we have continuous probability distributions, we have an infinite horizon. Yeah, we have infinitely many numbers. All numbers are possible, and we cannot list all of the possible numbers, obviously, because we have so many. Okay, the first form we're talking about is the uniform distribution. Can somebody tell me what shape the uniform distribution has? The formula, the function of the uniform distribution, what shape does it have? A what? Horizontal line? Almost. It's a rectangle. Yeah? So it looks like this. Okay? So you have your horizontal line, but you also have the ones on the side. And what is typical about any probability density functions is that they all engulf a specific area. What is the size of this area? 1. Yeah? That's really typical. The size of the area is always 1. That's with the uniform distribution, that's with the normal distribution, that's with the exponential distribution. Yeah, it's always equal to 1. And that also explains why our f of x is actually 1 over 30, because if we look at it, 1 over 30 times the width of the interval, which is also 30, that's equal to 1. Okay, now the probability that it's more than 55 minutes, so x larger than 55. In order to calculate that, we just look at the rectangle that kind of, that matches this criteria, so larger than 55 and smaller than 60. And we know it has a width of 5 and a length of 1 over 30. So multiply it out, and it's your probability. Next, we're looking for the probability that a student needs between 30 and 40 minutes. So again, we are looking at the field or the area now. So from 30 till 40 here, we know it has a width of 10 and a length of 1 over 30. Multiply it, and it's 33.33%. Okay, and now, what is the probability that the student completes the quiz in exactly 37.23 minutes? Anyone? Yeah?
0.
Exactly, it's 0, yeah? Because we have infinitely many possibilities in between 30 and 60, so any specific value, and you're asking for the probability of it, is 0. Okay? Because we're always just looking at intervals from now on. Yeah. Moving on from the uniform to the normal distribution. The normal distribution also has a very characteristic shape. What kind of a shape does it have? How does it look like? Anyone? It looks like bell-shaped, and it's symmetrical, right? It looks like this. Yeah? This is how a normal distribution looks like. And note that all normal distributions have a characteristic. In the middle, we have our average. In this case, it's 7.5. And the width of the normal distribution is determined by our standard deviation. Yeah? So the larger the standard deviation, the flatter the thingy is. And the smaller the standard deviation, the steeper it will be. So now we're looking for the probability of x being larger than 10. And one of the ways we can solve it is, or actually the main way we're going to solve it is to transform the x into a z statistic. So in order to do that, we are going to subtract our mean and divide by the standard deviation, which is actually the formula for the z statistics. So the x minus the x minus the mean divided by the standard deviation. This is the same as z. Yeah, it's just the formula for that. And we're doing that to both sides, so to x and to tan. So also 10 minus the mean divided by the standard deviation, the mean being 7.5, the standard deviation being 2.1. Yeah, and now we can reformulate it. We know this is equal to z, this is equal to 1.19, so we're looking for a z larger than 1.19. Yeah? The z statistic is used for something called the standard normal distribution. Yeah, there's a difference between the normal distribution and the standard normal distribution. The standard normal distribution has the characteristic that the mean is equal to 0 and the standard deviation is equal to 1. And the idea is that instead of using integral calculation to always calculate the areas below these bell-shaped curves, we can transform them into a standard normal distribution of which our percentages are known and from which we can read the values from the table. Yeah? So we always do this step, we convert into the z distribution. Okay, in this case, we're looking for z being larger than 1.19, which you can see here, the orange field. And also something I want to point out here, the z statistic only gives you values for smaller than a number. Yeah? Just like Poisson and binomial, it's always smaller than. So here, we have to use the complement rule, 1 minus the white area here. Okay, so this white area that you see here, that has a certain proportion that we don't know, but we can look it up in the table. And the value here is 10. So we would first transform the 10 into our z distribution, which is 1.19. Then we look up 1.19 in the table, which gives us this probability, this area, and then we do 1 minus this area in order to get the orange area. Yeah? So yeah, if you look at 1.19, that's 88.3% in the table. Should I show real quick how you do it with the table, or is it clear to everybody? Is it clear? Yeah, okay. All right, then I'll move on. Now we're looking for the probability that it's between 7 and 9 hours. So again, we're looking at an area that we want to calculate. Yeah? And once more, we first transform into the z distribution and subtract the mean, divide by the standard deviation. Do this with all the 3 components in the formula. And we will end up with z being between negative 0.24 and negative 7.1. And yeah, now same thing, same idea. We need to calculate the orange area, so we're going to first take the proportion of this big area that is smaller than 9 and subtract this white area which is smaller than 7. Yeah? To get the orange one. Is that clear? The area that's smaller than 9 minus the area that's smaller than 7 to get the orange one. And these probabilities we can look up in the table and it will be around 35.6%. Yeah? Okay, now the probability that the student spends less than 3 hours, same thing, exact same thing, so we're looking for an x value that's smaller than 3 and the probability of it. So first we do the z transformation, we transform into the z value. Through the same approach, we find out a z value of negative 2.14, look it up in the table, and have our matching probability. Yeah, in this case, 1.62%. Okay, so now we did it forward, and we're pretty much doing the same thing backwards now. So before we had our x value, based on the x value, we find the z value, and then we find the probability. Now we're doing it the inverse way. So we first have the probability. Based on the probability, we look up in the table our z value, and then we find our x. Yeah? Graphically, it looks like this. So we have our x value that we don't know. but we do know the area of the orange field. We know it's 5%. Yeah, so all we need to do is we need to look up in the table now the 5% and find the matching z-value. The z-value for the 5% on the left tail, the left-hand side is called the left tail, is actually written down as negative z of 0.05. Yeah, that's another way of writing down the left tail. If you would write down z of 0.05 positively without the negative sign, that means the right tail. Okay, so that's a thing I want to point out here. And yep, just look it up in the table. The value, it's going to be negative 1.645. That's the value for negative z of 0.05. And the value for positive z of 0.05 would then be positive 1.645. Yeah, because it's symmetrical, it's going to be the same. Only the plus and minus signs are going to be different. So yeah, now we have our z value. We want to still find our x value, so we're going to set it equal to this term here, x minus 7.5 divided by 2.1. Because this is how we always calculate the z value, right? We set it equal, and now we solve for our x by multiplying by 2.1 and adding 7.5, and our x is 4.05 hours. Yeah? I always recommend drawing the normal distributions and standard normal distributions because it really helps you to see which area you're looking at. So maybe get used to drawing it. It's gonna make your life easier. Okay, so if you remember what we did here now, we did it the inverse way, right? We had the probability, then we found z, then we found x. And that's exactly what this problem is like. It's the same thing, just formulated a little bit more complicated. So here, basically, we're dealing with a situation where we have a shop, yeah, and there's like demand coming in this shop, and we have an average weekly demand of 200 units. We also have a standard deviation of 30 units, and we want to find out how much do we need to have in stock so that the probability of running short is going to be less than 6%. So in other words, what is the reorder point going to be so that only less than 6% are going to be above this reorder point? If I draw it, it looks like this. Yeah? Same thing we had earlier. The only difference is now it's on the right-hand side. So now we're dealing with a right tail probability of 6% rather than a left tail probability of 6%. And we're looking for the x value, right? The x ROP, the x reorder point, for which the probability of the demand being higher than this x value is smaller than 6%. So same thing, we subtract our mean, divide by our standard deviation, and find the value for the z in our table. Yeah? And if you look it up now, make sure that you do not look up the z value for 6% in the table, because that would actually give you the left tail on the left side. Here. If you look up 6% in the table, it'll give you the left tail here, this area. Yeah? So in order to find this area, you actually need to look up the 94%, yeah, which is going to give you this entire area, 94. So the x for which any value lower has a probability of occurring of 94% chance. So you look up that value, and then you do 1, oh no, you don't even do 1 minus that. You just look up the value of 94%, and then you're done, yeah? So that's the big difference. That when we have a positive tail, just make sure you use the complement proportion. Yeah, and final step, we have our z value. We want to find out our x, so we set it equal to x minus 200 divided by 30, solve for our x, and you end up with rounded up to 247 as your reorder point. Yeah? Are there any questions? regarding this procedure? Clear? Okay, so now we're moving away from normal distribution over to exponential distributions. Here we have lambda, which is our rate of occurrence. Yeah, it's kind of similar to Poisson distribution, where we also had a rate. Now in this case, it's also a rate. We don't necessarily need to look at the interval anymore that is in the question. But what is important is to make sure that you're staying consistent. So when you're using hours or days, you need to stick with the same hour or day units. Yeah. So what I mean by that is, in the exponential random variable, we have our x and we have our lambda. These are the only two variables that we actually have. Make sure that your lambda and your x are both defined for the same units. So hours or minutes or whatever. Okay, so we're looking for the probability of x being larger than 2. And if you draw it graphically again, this is how an exponential distribution looks like. Main characteristic or main difference here between the exponential and the other distributions we covered is that here, when looking up the value, we need to look it up for larger than a specific value. So here we're looking for the area that is larger than A in this case. Yeah. Before, with the normal, Poisson, and binomial, we looked at values smaller than. Now it's larger than. So in order to find out x larger than 2, we just plug in 2 into the formula because it's larger than 2, right? So that's correct. And yeah, you just plug in your negative 0.3 as your lambda and your 2 as your A, and you get your answer. Now, if we want to look for x smaller than 4, we need to use the complement because now it's about smaller than, and it's actually defined for areas larger than A. So now use the complement 1 minus the probability of x being larger than 4. Yeah? And that's around 70% now if you fill in all the values and calculate it out. Next, the probability for x to be between two specific values, so between 1 and 2. Yeah, so we're looking at an interval now from A and B, from A to B. So we first calculate a probability of x being larger than 1, yeah, which is going to give us this entire big area. And then we subtract the small area, which is the probability for x being larger than 2, yeah, in order to get this orange field. Yeah, do you see that? Sorry, I don't have like the little pen thing here, but that's, so this big area, this entire big area, larger than A divided by larger than B, sorry, not divided, subtracted. No, the big area minus the small area, yeah? And you get the orange area. Okay. And then the last one, the probability of x being equal to 3. What is that? It's kind of a trick question because it's 0, yeah? Because we're dealing with continuous probabilities again, it's 0. Okay? So make sure we're always dealing with intervals. Okay, last one for today. So, again, exponential distribution, we have a mean of 5 minutes. Yeah, it takes 5 minutes for the service in a bank. And like I told you, we need to know our x, we need to know our lambda. Lambda is the rate. So what is going to be the rate if it takes 5 minutes for the service? What is the rate? And think about it, we don't do it in hours now. We say 5 minutes is our service time. So we're talking about minutes. You have to stay consistent. So how many are being served in 1 minute then? Here? Exactly, 1 divided by 5. A fifth of a customer is being served in 1 minute, yeah? If you would do it in hours, you would then, well, have to convert it differently. Okay, so first step, like I said, first find your lambda, in this case 0.2 customers per minute. And because we do it in minutes, we want to know the probability for x being smaller than 10 minutes, yeah? And because we know that the exponential distributions are valid for A being larger than a value, we are now again using the complement rule. Yeah, so 1 minus the probability of x being larger than 10, which is this entire area. This entire area minus the area in white that is above 10. And that should be around 86%. And now the last one, pay attention to this because it's also on the bonus. If you have a conditional situation, yeah, you have the situation given that 10 minutes have already passed and you've already provided service for 10 minutes. What is the probability that you're going to provide another additional 10 minutes of service? So this is like the probability tree we talked about. It's a conditional probability. What is the probability for x being larger than 20 given that it is actually larger than 10? Yeah? To solve this, we are actually looking at the area of x larger than 20, which would be around here. Let's say this is 20. So we're looking at the small area over here divided by the area that is larger than 10. So this area, yeah. I know it's kind of, hold on. Okay, so here we have 0, we have 10, we have 20. So we're looking at the area that is larger than 20 divided by the area that is larger than 10. So this, all of this including the one that is larger than 20. Yeah? You just plug in the values into the formula and then you should end up with 13.53%. But also important to point out here, we could have also done it in a different way, and this is actually called the law of no memory for the exponential distributions, because it doesn't really matter what happens before, it only matters what happens from now on. So based on the situation, we are actually thinking about, okay, what is the probability for 10 more minutes based on the fact that 10 minutes have already occurred before, which is the same as the probability of x being larger than 10. So the probability of 10 more minutes being necessary for the service to occur. Yeah, and this is known as the no memory rule. Yeah, so it means that the proportion of this small area divided by this big area is the same as the proportion of this area divided by this big area. Yeah? That's the proportion. And it's the same, and that's why we have the law of no memory. Yeah? So things like that you can calculate in two different ways, but obviously the second way is easier because you just need to find the probability of x being larger than 10. Okay? Any questions? Is it all clear? Still hungover? No?